Good morning to all. This is Anvej from AAA branch. Today my topic is about substations for future HVDC grids. First of all, what is HVDC technology? The HVDC is a well-established technology for grid reinforcement that avoids some of the disadvantages associated with AC transmission upgrades, increased AC system fault level, requirements for reactive power, and synchronized AC networks. By transmitting electrical energy over DC circuit, it has been used commercially for more than 60 years, mainly to transmit bulky power bulk power over large distance and connected asynchronous AC system, and it is a favorable choice when long undersea cable connections are needed. The HVDC transmission utilized power electronic converters to transform AC to DC and DC to AC. The converters utilized either thyristors or insulated gated bipolar transistor, that is IGBT power electronic switches. So thyristors are used in line communicated converters LCCS, the traditional HVDC technology, while IGBTs are used in voltage source converters, that is VSAs. While both technologies can provide fast control of active power and power transmission using overhead line or cable systems, there are different on the other. So on the one hand, LCCS, that is line communicated converters, are more mature, cost efficient and efficient technology for very large power ratings, so on the order of 10 gigawatt. Alternatively, the VSCS HVDC applications of the advantages, so including a smaller overall footprints, fast active power reversal capability, flexibility and independent control of reactive power, easier integration into weak power system, and use of extrude cables, for instance based on the cross-linked pylonethyl. Since the turn of the century, HVDC has been a revival in the countries such as China, India, and Brazil. LCC HVDC installation transport bulk power over long distance, fulfilling a need caused by fast economic growth. At the same time, the development of VSC technology led to new applications that include using submarine cables to interconnect oil platforms and offshore wind farms with onshore facilities, and underground cables and overhead line application provide land-based links. Recent advancement in VSC technology has enabled the development of HVDC grid with two or more converters connected in parallel. Several such systems has been developed on or under construction, whereas point-to-point systems are typically developed as project using an engineering procurement construction procedure. For the HVDC grids will in many cases be developed gradually, requirement interfaces among projects for different vendors, although LCC HVDC grids or hybrid VLCS or LCC HVDC grid share possible. This article focused on VSC HVDC grids, their substations layout and how they differ from their AC counterparts. The HVDC substation consists of a DC switchyard connecting multiple line or cable and possible one or more converter stations, as which as with the AC system device can be categorized as primary equipment which carries the power and secondary equipment interfacting and the control. Primary equipment. In a further DC substation, the primary equipment could consist of various components of power transfer, protection and switching capabilities for system reconfiguration, perspective components including AC DC converters, circuit breakers and other switchgear cables lines, and their terminations means of discharge cables and equipment to control power. AC-DC converters. Converting AC to DC is an essential requirement for the power system of the future, enabling the connection of HVDC system to existing AC transmission network for bulk energy transfer. A VSC station consists of HVSC valve hall in which the electronic equipment is placed, as well as phase inductors and measurement equipment. The AC transformers and switchyards are typically placed outside the VSC area. Substations. Various VSC technology can be used for AC-DC conversion in multi-terminal system, which can be roughly classified into two types: the DC fault feedings and the DC fault blocking. Both types can control the DC side current during normal operations. However, they can differentiate by their DC fault response. So next, circuit breakers and switchgear. With a DC substation, there are several requirements for switching, which can be grouped according to functionality: grounding, disconnecting, current communication, and current interruption. Fault current interruption devices are at the DC side are essential to achieve selective protection of multi-terminal HVDC system by isolating only the fault element. The requirement for interrupting a DC current lead to challenges with HVDC circuit breaker, and it is not observed in AC system. The absence of natural recurring current zero crossing requires the HVDC circuit breaker to drive the DC fault current towards zero and absorbs the energy that remains in the system at the moment the circuit breaker opens. To perform these functions, an HVDC circuit breaker typically make use of parallel path with auxiliary circuits to enable current communication and energy absorption. In addition, the high switches speeds require fast mechanic operations of power electronic switches in the circuit. Recently, the breakers can operate within 2 to 10 ms of an order of magnitude faster than the equivalent. Next, the energy dissipation. There is often of a requirement for discharge cables and overhead line, either for safety when taking line out of service, for maintenance, for dissipating excess energy during a momentary fault from wind farm for which power cannot be instantaneously decreased, or for balance and equal pole voltages in system in symmetric monopolar network. For plant maintenance, a grounding switches can be utilized, which could take seconds to discharge the line and reopen. This is acceptable given that is operation has no stringent time constraints. In the case of pole balancing, however, there is a requirement to resume power flow as quick as possible or continue normal operations. Different solutions based on the power electronics or nonlinear resistors have been suggested to meet these demands. So next, DC power flow control devices. So the uh, controlling the power flow enables the use of any power system at its full capability, the topology and configuration of passive networks, and the voltages at each node determine the power flow unless active devices are applied. Which flexible AC transmission system already dynamically control power flow in AC grids. There are currently no commercial available product for HVDC grids. In a HVDC grid, the voltage difference and resistance between two nodes determine the power flow through a transmission line. Therefore, the power flow can be controlled by adding resistance, although incurring additional losses would be unattractive, or modifying the node voltages at each end of the line. On a meshed system, for the which each node voltage affects the power flow on multiple lines, it is not possible to maximize the power flow on all lines, resulting in some line invertible being underutilized. Some insert of a controllable voltages in series with a line with the observable energy transferred using an equivalent but opposing voltages. The voltages requirement would be similar voltage drop across the line, small compared with the pole to ground voltages. Next, the DC to DC converters. The transferring energy between different DC voltages require a different solution compared the AC transformer, which provides the effective passive voltage transformation. While there are no HVDC DC to DC converters in operation today, there could be benefits in connection HVDC system or different voltages. An example would be increased operational flexibility by interconnecting networks they were built at different times. DC to DC converters could either be directly connected or provided galvanic isolation when using a intermediate AC stage. Further, they would also have the ability to control power flow, as DC to DC converter might also be able to prevent a fault from propagating across the network, although this may cause additional costs. So secondary equipments. The secondary equipments in DC substations can be expected to require more computational power and communications that is in AC substations, give the greater complexities of many controls protection functions needed to operation and HVDC grids. So the measurement device, the conventional instrument transformer based on the electromagnetic induction technologies are the most widely used primary sensor in AC grids. The bandwidth of such transformer is usually limited to a few kilohertz. As beyond these frequencies, the conversion ratio of these devices is nonlinear due to resonance and capacitive coupling. For HVDC applications, non-conventional instrument transformers must be zero flux current sensors, combined shunt and Rogowski coil and fiber optical current sensors can be used to measure currents in HVDC grids. Resistor capacitive voltage divider technology is most commonly adopted for HVDC voltage measurement. The future trend of NC-ITS for HVDC grids includes compact and possible integrated optional options through moderate technologies such as RC devices for gas insulated switchgears and integrated optical sensors. Compared to a substation, a large number of current and voltage instrument transforms are likely to use DC substations. Those substations can contain more components that must be control or protection converters. DC lines, indicators, and HVDC circuit breakers in additional substations are interfaced with merging units with digitize the measured. Next, the control. The HVDC grid control ensures the stable operational by controlling the DC voltages, which presents itself as a global parameter with the grid. Many DC voltages control approaches are expected to be used for HVDC grids, which can be divided into centralized and disturbed approaches, in which in the centralized approach on converter responsible for the control of direct voltage act as a DC slave bus, which the other converters regulate active power. This approach is not suitable for large HVDC grids because depends upon single slave converter could lead to relatable issues. In the disturbed approach, all the converters in HVDC grid control share the active power balance by employing a voltage drop scheme. However, this requires a coordination among the substation controls and HVDC grid controls. The disturbed approaches is more appropriate for large HVDC grids but can also be used for smaller HVDC grids if needed. HVDC substations controls are relatively fast regulators that include prime voltage power control station in HVDC grid. This control may take the form of voltage drop characteristics enable automatic power sharing among several controls with a dependent of communication. Next, the summary. Although the design principle of for a AC substation, such as substation layout, are in the theory application to the design of substation, fundamental differences exist and depend on the choice made in the system topology, control, and protection. First, the HVDC grid topology determines the number of transmission lines to route with a DC substation. The primary and secondary equipments required within the DC substation, and its characteristics depend upon the adapted control and protection physiology. In addition, the location of the substation influence the choice made in the construction and installation technology. Recent technological developments indicate the most building blocks for the future HVDC grids and place are advancing towards a practical realization. Nevertheless, the constructions of reliable and the cost efficient of HVDC parameters. Engineers to consider the many optional for system protection operation and implicate that these have on practical realization of underlying the DC substations. Thank you.